Digital audio broadcasting is a digital radio technology for broadcasting radio stations, used in several countries, particularly in Europe. As of 2006, approximately 1,002 stations worldwide broadcast in the DAB format. The DAB standard was initiated as a European research project in the 1980s. The Norwegian Broadcasting Corporation launched the very first DAB channel in the world on June 1, 1995, and the BBC and ESA launched their first DAB digital radio broadcasts in September 1995. DAB receivers have been available in many countries since the end of the 1990s. DAB may offer more radio programs over a specific spectrum than analog FM radio. DAB is more robust with regard to noise and multipath fading for mobile listening, since DAB reception quality first degrades rapidly when the signal strength falls below a critical threshold, whereas FM reception quality degrades slowly with the decreasing signal. Audio quality varies depending on the bit rate used and audio material. Most stations use a bit rate of 128 kbits or less with the MP2 audio codec, which requires 160 kbits to achieve perceived FM quality. 128 kbits gives better dynamic range or signal-to-noise ratio than FM radio, but a more smeared stereo image, and an upper cutoff frequency of 14 kHz, corresponding to 15 kHz of FM radio. However, CD sound quality with MP2 is possible with 256-192 kbps. An upgraded version of the system was released in February 2007, which is called DAB+. DAB is not forward compatible with DAB+, which means that DAB-only receivers are not able to receive DAB+ broadcasts. However, broadcasters can mix DAB and DAB+ programs inside the same transmission and so make a progressive transition to DAB+. DAB+ is approximately twice as efficient as DAB due to the adoption of the AAC+ audio codec, and DAB+ can provide high-quality audio with bit rates as low as 64 kbits. Reception quality is also more robust on DAB+ than on DAB due to the addition of Reed-Solomon error correction coding. In spectrum management, the bands that are allocated for public DAB services are abbreviated with TDAB, where the T stands for terrestrial. More than 20 countries provide DAB transmissions, and several countries, such as Australia, Italy, Malta, Switzerland and Germany, are transmitting DAB+ stations. See countries using DAB-DMB. However, DAB radio has still not replaced the old FM system in popularity. History: DAB has been under development since 1981 at the Institut für One-Quarter Rundfunk technique. In 1985 the first DAB demonstrations were held at the WARCORB in Geneva, and in 1988 the first DAB transmissions were made in Germany. Later DAB was developed as a research project for the European Union, which started in 1987 on initiative by a consortium formed in 1986. The MPEG-1 Audio Layer 2 codec was created as part of the EU 147 project. DAB was the first standard based on orthogonal frequency division multiplexing modulation technique, which since then has become one of the most popular transmission schemes for modern wideband digital communication systems. A choice of audio codec, modulation and error correction coding schemes and first trial broadcasts were made in 1990. Public demonstrations were made in 1993 in the United Kingdom. The protocol specification was finalized in 1993 and adopted by the ITU, a standardization body, in 1994, the European Community in 1995 and by ETSI in 1997. Pilot broadcasts were launched in several countries in 1995. The UK was the first country to receive a wide range of radio stations via DAB. Commercial DAB receivers began to be sold in 1999 and over 50 commercial and BBC services were available in London by 2001. By 2006, 500 million people worldwide were in the coverage area of DAB broadcasts, although by this time sales had only taken off in the United Kingdom and Denmark. In 2006 there were approximately 1,000 DAB stations in operation worldwide. The standard was coordinated by European DAB Forum, formed in 1995 and reconstituted to the World DAB Forum in 1997, which represents more than 30 countries. In 2006 the World DAB Forum became the World DMB Forum, which now presides over both the DAB and DMB standard. In October 2005, the World DMB Forum instructed its technical committee to carry out the work needed to adopt the AAC Plus audio codec and stronger error correction coding. This work led to the launch of the new DAB Plus system. Technology, bands and modes. DAB uses a wide bandwidth broadcast technology and typically spectra have been allocated for it in band 3 and L band, although the scheme allows for operation almost anywhere above 30 MHz. The U.S. military has reserved L band in the USA only, blocking its use for other purposes in America, and the United States has reached an agreement with Canada to restrict L band DAB to terrestrial broadcast to avoid interference. DAB has a number of country-specific transmission modes. For worldwide operation, a receiver must support all four modes: Mode I for band 3, Earth; Mode 2 for L band, Earth and satellite; Mode 3 for frequencies below 3 GHz, Earth and satellite; Mode 4 for L band, Earth and satellite. Protocol stack. From an OSI model protocol stack viewpoint, the technologies used on DAB inhabit the following layers. The audio codec inhabits the presentation layer. Below that is the data link layer, in charge of statistical time division multiplexing and frame synchronization. Finally, the physical layer contains the error correction coding, OFDM modulation, and dealing with the over-the-air transmission and reception of data. Some aspects of these are described below. Audio codec, the older version of DAB that is being used in Denmark, Ireland, Norway, Switzerland and the UK, uses the MPEG-1 audio layer 2 audio codec, which is also known as MP2 due to computer files using those characters for their file extension. The new DAB Plus standard has adopted the HEAAC version 2 audio codec, commonly known as AAC Plus or AAC Plus. AAC Plus is approximately 3 times more efficient than MP2, which means that broadcasters using DAB Plus will be able to provide far higher audio quality or far more stations than they can on DAB, or, as is most likely, a combination of both higher audio quality and more stations will be provided. One of the most important decisions regarding the design of a digital radio system is the choice of which audio codec to use, because the efficiency of the audio codec determines how many radio stations can be carried on a multiplex at a given level of audio quality. The capacity of a DAB multiplex is fixed, so the more efficient the audio codec is, the more stations can be carried, and vice versa. Similarly, for a fixed bit rate level, the more efficient the audio codec is, the higher the audio quality will be. Error correction coding. Error correction coding is an important technology for a digital communication system because it determines how robust the reception will be for a given signal strength. Stronger ECC will provide more robust reception than a weaker form. The old version of DAB uses punctured convolutional coding for its ECC. The coding scheme uses unequal error protection, which means that parts of the audio bit stream that are more susceptible to errors causing audible disturbances are provided with more protection and vice versa. However, the UEP scheme used on DAB results in there being a gray area in between the user experiencing good reception quality and no reception at all, as opposed to the situation with most other wireless digital communication systems that have a sharp digital cliff, where the signal rapidly becomes unusable if the signal strength drops below a certain threshold. When DAB listeners receive a signal in this intermediate strength area, they experience a burbling sound which interrupts the playback of the audio. The new DAB Plus standard has incorporated Reed-Solomon ECC as an inner layer of coding that is placed around the byte interleaved audio frame but inside the outer layer of convolutional coding used by the older DAB system. Although on DAB Plus the convolutional coding uses equal error protection rather than UEP since each bit is equally important in DAB Plus. This combination of Reed-Solomon coding as the inner layer of coding, followed by an outer layer of convolutional coding. So-called concatenated coding became a popular ACC scheme in the 1990s, and NASA adopted it for its deep space missions. One slight difference between the concatenated coding used by the DAB+ system and that used on most other systems is that it uses a rectangular byte interleaver rather than Forney interleaving in order to provide a greater interleaver depth, which increases the distance over which error bursts will be spread out in the bit stream, which in turn will allow the Reed-Solomon error decoder to correct a higher proportion of errors. The ECC used on DAB+ is far stronger than is used on DAB, which, with all else being equal, would translate into people who currently experience reception difficulties on DAB receiving a much more robust signal with DAB+ transmissions. It also has a far steeper digital cliff, and listening tests have shown that people prefer this when the signal strength is low compared to the shallower digital cliff on DAB. Modulation immunity to fading and inter-symbol interference is achieved without equalization by means of the OFDM and EQ-PSK modulation techniques. For details, see the OFDM system comparison table. Using values for the most commonly used transmission mode on DAB, transmission mode I. The OFDM modulation consists of 1,536 subcarriers that are transmitted in parallel. The useful part of the OFDM symbol period is 1 millisecond, which results in the OFDM subcarriers each having a bandwidth of 1 kHz due to the inverse relationship between these two parameters, and the overall OFDM channel bandwidth is 1,537 kHz. The OFDM guard interval for TMI is 246 microseconds, which means that the overall OFDM symbol duration is 1.246 milliseconds. The guard interval duration also determines the maximum separation between transmitters that are part of the same single-frequency network, which is approximately 74 km for TMI single-frequency networks. OFDM allows the use of single-frequency networks, which means that a network of transmitters can provide coverage to a large area, up to the size of a country, where all transmitters use the same transmission frequency. Transmitters that are part of an SFN need to be very accurately synchronized with other transmitters in the network, which requires the transmitters to use very accurate clocks. When a receiver receives a signal that has been transmitted from the different transmitters that are part of an SFN, the signals from the different transmitters will typically have different delays, but to OFDM they will appear to simply be different multipaths of the same signal. Reception difficulties can arise, however, when the relative delay of multipath exceeds the OFDM guard interval duration, and there are frequent reports of reception difficulties due to this issue when there is a lift, such as when there's high pressure, due to signals traveling farther than usual, and thus the signals are likely to arrive with a relative delay that is greater than the OFDM guard interval. Low-power gap-filler transmitters can be added to an SFN as and when desired in order to improve reception quality, although the way SFNs have been implemented in the UK up to now they have tended to consist of higher power transmitters being installed at main transmitter sites in order to keep costs down. Bit rates. An ensemble has a maximum bit rate that can be carried, but this depends on which error protection level is used. However, all DAB multiplexes can carry a total of 864 capacity units. The number of capacity units, or CU, that a certain bit rate level requires depends on the amount of error correction added to the transmission, as described above. In the UK, most services transmit using protection level 3, which provides an average ECC code rate of approximately 1/2, equating to a maximum bit rate per multiplex of 1184 kbits. Services and ensembles. Various different services are embedded into one ensemble. These services can include primary services, like main radio stations, secondary services, like additional sports commentaries, data services, electronic program guide, collections of HTML pages and digital images, slideshows, which may be synchronized with audio broadcasts. For example, a police appeal could be broadcast with the EFIT of a suspect or CCTV footage. Video, Java platform applications, IP tunneling, other raw data. DAB+, the term DAB most commonly refers both to a specific DAB standard using the MP2 audio codec, but can sometimes refer to a whole family of DAB-related standards, such as DAB+, DMB and DAB-IP. DAB+, World DMB, the organization in charge of the DAB standards, announced DAB+, a major upgrade to the DAB standard in 2006, when the HEAAC v2 audio codec was adopted. The new standard, which is called DAB+, has also adopted the MPEG surround audio format and stronger error correction coding in the form of Reed-Solomon coding. DAB+ has been standardized as ETS-ITS 102.563. As DAB is not forward compatible with DAB+, older DAB receivers cannot receive DAB+ broadcasts. However, DAB receivers that will be able to receive the new DAB+ standard via a firmware upgrade went on sale in July 2007. If a receiver is DAB+ compatible, there will be a sign on the product packaging. DAB+ broadcasts have launched in several countries like Australia, Czech Republic, Germany, Hong Kong, Italy, Malta, Norway, Poland, Switzerland, and the Netherlands. Malta was the first country to launch DAB+ in Europe. Several other countries are also expected to launch DAB+ broadcasts over the next few years, such as Austria, Hungary and Asian countries, such as Thailand, Vietnam and Indonesia. If DAB+ stations launch in established DAB countries, they can transmit alongside existing DAB stations that use the older MPEG-1 audio Layer 2 audio format, and most existing DAB stations are expected to continue broadcasting until the vast majority of receivers support DAB+. Ofcom in the UK has published a consultation with the intention to set up a new multiplex containing a mix of DAB and DAB+ services, with the intention of moving services to this format in the long term. DMB. Digital multimedia broadcasting and DAB-IP are suitable for mobile radio and TV both because they support MPEG-4 AVC and WMV9 respectively as video codecs. However, a DMB video subchannel can easily be added to any DAB transmission, as it was designed to be carried on a DAB subchannel. DMB broadcasts in Korea carry conventional MPEG-1 Layer 2 DAB audio services alongside their DMB video services. Norway, South Korea and France are countries currently broadcasting DMB. Countries using DAB. More than 30 countries provide DAB, DAB+ and/or DMB broadcasts either as a permanent technology or as test transmissions. DAB and AM/FM compared, traditionally radio programs were broadcast on different frequencies via AM and FM, and the radio had to be tuned into each frequency, as needed. This used up a comparatively large amount of spectrum for a relatively small number of stations, limiting listening choice. DAB is a digital radio broadcasting system that through the application of multiplexing and compression combines multiple audio streams onto a relatively narrow band centered on a single broadcast frequency called a DAB ensemble. Within an overall target bit rate for the DAB ensemble, individual stations can be allocated different bit rates. The number of channels within a DAB ensemble can be increased by lowering average bit rates, but at the expense of the quality of streams. Error correction under the DAB standard makes the signal more robust but reduces the total bit rate available for streams. FM HD radio versus DAB. Some countries have implemented Eureka 147 digital audio broadcasting. DAB broadcasts a single station that is approximately 1500 kHz wide. That station is then subdivided into multiple digital streams of between 9 and 12 programs. In contrast, FM HD radio shares its digital broadcast with the traditional 200 kHz wide channels, with capability of 300 kbits per station. The first-generation DAB uses the MPEG-1 audio Layer 2 audio codec which has less efficient compression than newer codecs. The typical bitrate for DAB programs is only 128 kbits and as a result most radio stations on DAB have a lower sound quality than FM, prompting a number of complaints among the audiophile community. As with DAB+ or TDMB in Europe, FM HD radio uses a codec based upon the MPEG-4 HEAAC standard. HD radio is proprietary system from the company Ubiquiti. DAB is an open standard deposited at ETSI. User frequency spectrum and transmitter sites. DAB gives substantially higher spectral efficiency, measured in programs per megahertz and per transmitter site, than analog communication. This has led to an increase in the number of stations available to listeners, especially outside of the major urban areas. Numerical example, analog FM requires 0.2 MHz per program. The frequency reuse factor in most countries is approximately 15, meaning that only 1 out of 15 transmitter sites can use the same channel frequency without problems with co-channel interference, that is crosstalk. Assuming a total availability of 102 fathoms channels at a bandwidth of 0.2 MHz over the band 2 spectrum of 87.5 to 108.0 MHz, an average of 102/15 equals 6.8 radio channels are possible on each transmitter site. This results in a system spectral efficiency of 1/15 equals 0.30 programs MHz. DAB with 192 kbits codec requires 1.536 MHz. 192 kbits/1136 kbits equals 0.26 MHz per audio program. The frequency reuse factor for local programs and multi-frequency broadcasting networks is typically 4 or 5, resulting in January 4th equals 0.96 programs MHz. This is 3.2 times as efficient as analog FM for local stations. For single-frequency network transmission, for example of national programs, the channel reuse factor is 1, resulting in 10.25 MHz equals 3.85 programs MHz, which is 12.7 times as efficient as FM for national and regional networks. Note the above capacity improvement may not always be achieved at the L-band frequencies, since these are more sensitive to obstacles than the FM band frequencies, and may cause shadow fading for hilly terrain and for indoor communication. The number of transmitter sites or the transmission power required for full coverage of a country may be rather high at these frequencies, to avoid that the system becomes noise limited rather than limited by co-channel interference. Sound quality. The original objectives of converting to digital transmission were to enable higher fidelity, more stations and more resistance to noise, co-channel interference and multipath than in analog FM radio. However, the leading countries in implementing DAB on stereo radio stations use compression to such a degree that it produces lower sound quality than that received from non-mobile FM broadcasts. This is because of the bit rate levels being too low for the MPEG Layer 2 audio codec to provide high-fidelity audio quality. The BBC Research and Development Department states that at least 192 kbits is necessary for a high-fidelity stereo broadcaster, when BBC in July 2006 reduced the bit rate of transmission of Radio 3 from 192 kbits to 160 kbits. The resulting degradation of audio quality prompted a number of complaints to the corporation. BBC later announced that following this testing of new equipment, it would resume the previous practice of transmitting Radio 3 at 192 kbits whenever there were no other demands on bandwidth. Despite the above, a survey of DAB listeners has shown most find DAB to have equal or better sound quality than FM. Notwithstanding the above, BBC Radio 4 has extended the periods it broadcasts programs with a lower bit rate and in mono in 2012, such as the Today program, rather than 128 kbits and in stereo. Programs which had traditionally been broadcast on BBC Radio 4 DAB in stereo, can now only be heard in the evenings in mono, even though the same programs still go out in stereo on Radio 4 Fathoms, digital TV and online. The BBC have issued a statement stating that stereo is still their default for BBC Radio 4 DAB, however after the Olympics, this does not appear to be the case in the evenings, making FM broadcasts superior. As very few car radios are currently fitted with DAB if the BBC switch FM offers indicated later in the decade, some listeners may be forced to receive mono broadcasts in the future, a somewhat backward step. An audio quality comparison of PCM, DAB, DAB+, FM and AM as available here. Benefits of DAB. Current AM and FM terrestrial broadcast technology is well established, compatible, and cheap to manufacture. Benefits of DAB over analog systems are explained below. Improved features for users. DAB radios automatically tune to all the available stations, offering a list for the user to select from. DAB can carry radio text from the station giving real-time information such as song titles, music type and news or traffic updates. Advanced program guides can also be transmitted. A similar feature also exists on FM in the form of the RDS. DAB receivers can display time of day as encoded into transmissions, so is automatically corrected when traveling between time zones and when changing to or from daylight saving. This is not implemented on all receivers, and some display time only when in standby mode. Some radios offer a pause facility on live broadcasts, caching the broadcast stream on local flash memory, although this function is limited. More stations. DAB is not more bandwidth efficient than analog measured in programs per megahertz of a specific transmitter. However, it is less susceptible to code-channel interference, which makes it possible to reduce the reuse distance, that is use the same radio frequency channel more densely. The system spectral efficiency is a factor 3 more efficient than analog FM for local radio stations, as can be seen in the above numerical example. For national and regional radio networks, the efficiency is improved by more than an order of magnitude due to the use of SFNs. In that case, adjacent transmitters use the same frequency. In certain areas particularly rural areas the introduction of DAB gives radio listeners a greater choice of radio stations. For instance, in South Norway, radio listeners experienced an increase in available stations from 6 to 21 when DAB was introduced in November 2006. Reception quality. The DAB standard integrates features to reduce the negative consequences of multipath fading and signal noise, which affect existing analog systems. Also, as DAB transmits digital audio, there is no hiss with a weak signal, which can happen on FM. However, radios in the fringe of a DAB signal can experience a bubbling mud sound interrupting the audio or the audio cutting out altogether. Due to sensitivity to Doppler shift in combination with multipath propagation, DAB reception range is reduced when traveling speeds of more than 120 to 200 km per hour, depending on carrier frequency. Less undocumented station interference. The specialized nature and cost of DAB broadcasting equipment provide barriers to undocumented stations broadcasting on DAB. In cities such as London with large numbers of undocumented radio stations broadcasting on FM, this means that some stations can be reliably received via DAB in areas where they are regularly difficult or impossible to receive on FM due to undocumented radio interference. Variable bandwidth, mono talk radio, news and weather channels and other non-music programs need significantly less bandwidth than a typical music radio station, which allows DAB to carry these programs at lower bit rates, leaving more bandwidth to be used for other programs. However, this had led to the situation where some stations are being broadcast in mono. See music radio stations broadcasting in mono for more details. Transmission costs. It is common belief that DAB is more expensive to transmit than FM. It is true that DAB uses higher frequencies than FM and therefore there is a need to compensate with more transmitters, higher radiated powers, or a combination, to achieve the same coverage. However, the last couple of years has seen significant improvement in power efficiency for DAB transmitters. This efficiency originates from the ability a DAB network has in broadcasting more channels per network. One network can broadcast 6 to 10 channels or 10 to 16 channels. Hence, it is thought that the replacement of FM radios and FM transmitters with new DAB radios and DAB transmitters will not cost any more as opposed to newer FM facilities. Lower transmission costs are supported by independent network studies from Terracom and SSRSRG. Among other things, they show that DAB is as low as 1/6 of the cost of FM transmission. Disadvantages of DAB: reception quality. The reception quality on DAB can be poor even for people who live well within the coverage area. The reason for this is that the old version of DAB uses weak error correction coding, so that when there are a lot of errors with the received data, not enough of the errors can be corrected and a bubbling mud sound occurs. In some cases a complete loss of signal can happen. This situation will be improved upon in the new DAB standard that uses stronger error correction coding and as additional transmitters are built. Audio quality. Broadcasters have been criticized for squeezing in a unregistered trademark more stations per ensemble than recommended, by minimizing the bit rate to the lowest level of sound quality that listeners are willing to tolerate, such as 112 kbits for stereo and even 48 kbits for mono-speech radios such as LBC 1152 and The Voice of Russia. Having few digital channels broadcasting in stereo. Signal delay. The nature of a SFN is such that the transmitters in a network must broadcast the same signal at the same time. To achieve synchronization, the broadcaster must counter any differences in propagation time incurred by the different methods and distances involved in carrying the signal from the multiplexer to the different transmitters. This is done by applying a delay to the incoming signal at the transmitter based on a timestamp generated at the multiplexer, created taking into account the maximum likely propagation time, with a generous added margin for safety. Delays in the receiver due to digital processing add to the overall delay perceived by the listener. The signal is delayed by 2 to 4 seconds depending on the decoding circuitry used. This has disadvantages. DAB radios are out of step with live events, so the experience of listening to live commentaries on events being watched is impaired. Listeners using a combination of analog and DAB radios will hear a confusing mixture when both receivers are within earshot. Time signals, on the contrary, are not a problem in a well-defined network with a fixed delay. The DAB multiplexer adds the proper offset to the distributed time information. The time information is also independent from the audio decoding delay in receivers since the time is not embedded inside the audio frames. This means that built-in clocks in receivers will be spot-on. Coverage. As DAB is at a relatively early stage of deployment, DAB coverage is poor in nearly all countries in comparison to the high population coverage provided by FM. An exception is Norway, as the country will have 99.5% coverage by the end of 2014. Compatibility. In 2006 tests began using the much improved HEAAC codec for DAB+. Virtually none of the receivers made before 2008 support the new codec, however, thus making them partially obsolete once DAB+ broadcasts begin and completely obsolete once the old MPEG-1 Layer 2 stations are switched off. New receivers are both DAB and DAB+ compatible. However, the issue is exacerbated by some manufacturers disabling the DAB+ features on otherwise compatible radios to save on licensing fees when sold in countries without current DAB+ broadcasts. Power requirements. As DAB requires digital signal processing techniques to convert from the received digitally encoded signal to the analog audio content, the complexity of the electronic circuitry required to do this is high. This translates into needing more power to effect this conversion than compared to an analog FM to audio conversion, meaning that portable receiving equipment will tend to have a shorter battery life, or require higher power. This means that they use more energy than analog Band 2 VHF receivers. As an indicator of this increased power consumption, some radio manufacturers quote the length of time their receivers can play on a single charge. For a commonly used FM DAB receiver from manufacturer Pure, this is stated as DAB 10 hours, FM 22 hours. Use of licensed codecs. The use of MPEG previously and later AAC has prompted criticism of the fact that a public system is financially supporting a private company. In general, an open system will permit equipment to be bought from various sources in competition with each other, but by selecting a single vendor of codec, with which all equipment must be compatible, this is not possible. FM radio switch off. No country has so far announced a complete switch off of FM radio stations. At the World DMB seminar held in Riva del Garda, Italy, April 14, 2013, it was announced that in Norway there will be 99.5% DAB coverage by 2014, and that the country is planning to switch off its national and regional FM radio services in 2017. There is no intention of switching off local FM services in Norway by that date, and no subsequent date has been announced for such a move. Other Nordic countries like Denmark and Sweden are evaluating a switch-off within 2022. UK is considering a progressive switch-off in the period 2017 to 2022. See also, ATSC standards, digital audio radio service, digital multimedia broadcasting, digital radio, digital television, digital radio mondiale, ETSI satellite digital radio, FM extra, HD radio, Internet radio device, ISDB, open cable, orthogonal frequency division multiplexing, satellite radio, Sirius XM satellite radio, spectral efficiency comparison table, TDMB, teletext, references. ETSI specifications available at ETSI Publications Download Area, pda.etsy.org, stot, jh. The How and Why of COFDM, BBC Research Development, external links, ETSI EN 300-401 v1.4.1, original DAB specification, etsy.org, ETSI TS 102-563 v1.1.1, DAB Plus enhancement specification, etsy.org, World DAB Forum, wordldab.org, DAB Ensembles Worldwide, whanaut.org,